Okay, so the bottom line here is that when you add a continuous distribution of wave number values, okay, a continuous distribution of waves, an infinite number of waves with a continuous distribution of wave number values, okay, centered about some number. In this case, this is a Gaussian packet, but just in general, if you have some continuous distribution of wave numbers, then you can make a single wave packet, okay? And this Gaussian distribution of k values, that is this wave packet with the Gaussian envelope, actually has very special properties. Okay, so in general, we can a wave packet can be written as an integral over amplitudes of an amplitude. Okay, the amplitude is what's multiplying k here. Okay, so the amplitude is a of k is just the distribution of k values. Okay, times some harmonic function, and in the most general case, we would write this as e to the I kx minus omega t. Okay, so we would write a a, uh, a complex number which is harmonic and which has real and imaginary parts. We're just looking at the real part here. Okay, and if we integrate that over k values from 0 to infinity, then we get then we can get any arbitrary function. So depending on what the distribution a of k looks like, that will dictate what your wave function looks like. Okay, what your waveform looks like, or your wave packet. Now, in the previous view graph, we talked about a Gaussian wave packet, and in that case, the distribution, the a of k, okay, distribution of k values has this Gaussian form. Okay, so this part here, e to the minus k naught squared divided by 2 sigma k squared, is a Gaussian function. Generally speaking, a Gaussian has a form of e to the minus a times some variable squared. Okay, where that variable can be a spatial variable, it can be a wave number variable, and so here we have it as it's a wave number variable, and so you can a is equal to, in this case, minus 1/2 sigma k squared. Okay, and so this is the Gaussian function, and then this is a normalization constant, which basically comes from the fact that, loosely speaking, if we interpret the square of this amplitude the square of this wave function in the complex conjugate sense, if we square that, we get a probability distribution. We'll discuss that in one of the next lectures. And so, what if we interpret wave packet as the probability distribution of of where the particle is, then we know it has to be somewhere in space. And so, if we integrate over all space, okay, then the net probability has to be equal 1. That means that the particle, the wave packet, has to be somewhere. And when you do this, you basically get a normalization constant which comes out, and that's basically where this comes from. So this is a very hand-wavy, loose thing so far. We haven't defined this very precisely. Okay, so take this with a little grain of salt, but that's the general way you proceed. Okay, so if we have this sort of Gaussian wave packet, or this Gaussian function, Gaussian distribution for the wave number values, then it can be shown that at time equals 0, or if you just freeze time, that the function, the actual spatial wave function, takes on the form something which looks very much like a sub k, except for now we replace sigma k with sigma x, okay, and k naught with x and x naught. Okay, so this is now in real space. So it's this envelope function times cosine kx, which provides the wiggles. So we have this envelope which is modulating the harmonic wave.